Okay, so let's do what we didn't do yet. Great. So I was just going to go through the ones that I didn't do in order. So let's start with number 8. We have these limits. The first one. So, yeah, the first thing we should do, which is this is so easy to forget, is to just try plugging in 0, 0, or at least in your head try it. I'm going to get 0 over 0, though, so that's no good, but you want to think about that first. So that means that we're going to need to do something, and with these types of limits, especially, like, we're very used to seeing x squared plus y squared on the bottom, or maybe with a square root or whatever on it. My advice is to convert these to polar. So this turns into what we write is the limit as r goes to 0, because xy is going to the origin, which is when r equals 0. And let me convert this. So this is r squared underneath the square root, and x is r cosine theta. Let me just simplify this. So this is an r, and that'll cancel that r, so I just get cosine theta. And this is right. So when I write a thing like this and we're in polar coordinates and there's actually two variables, r and theta, I just write the limit as r goes to 0, but what's happening with theta is a little bit like we have to hold this in our minds as we do this. Theta could be anything. Theta could even depend on r. Theta could take different values, and in this case, r is completely gone, so it hardly matters that r is going to 0. The fact that this still depends on theta and there's no r's means that this does not exist. This is like saying that if theta takes different values, then we're going to get different answers for our limit, like depending on whatever the cosine of theta is. So this one does not exist. So yeah, this is the first one. The second one from number 8 is similar. This time I have x times y over this. Okay, first things first, let's at least imagine plugging in 0, 0. Clearly I'm going to get 0 on the bottom. I also get 0 on the top. Oh well, we tried. Let's try the next thing, convert to polar. So this is almost exactly like before. So x is r cosine theta, y is r sine theta. Yeah, I'm not writing very well, but sure, like that. So this is just an r, and so that's going to cancel with one of my r's from the top. So now I have r sine theta cosine theta. And so here's how this one's different from the last one. There's still r's. After the smoke clears, there's still r's. There weren't when we were doing the last one. It was only thetas. So here's what I'm going to say about this one. And you've seen me do this before. I see part that depends on r and part that depends on theta. This part is going to 0. This part, the important part about it is that it's bounded. Sine and cosine are always between -1 and 1. So there's a limit to how big those can be and how small those can be. If I take r, which is going to 0, and I multiply it by something, and this is still like the last one where I have to imagine that theta could be anything and theta could even depend on r, but in this case it doesn't matter because this stuff is always between -1 and 1, and I'm multiplying it by something that's going to 0. So I get 0. Next one, I've got this limit as x, y goes to 0, 0, sine of x plus y over x minus y minus 1. And what's the first thing we always try? We always just try plugging in 0 for x and y. I mean, if they're going to 0, 0. And this time I'm not going to get 0 on the bottom. So this is why we try this. Because when it's going to work, it just gives us our answer straight there. So sine of 0 is 0, -1 on the bottom, you get 0. Oops, that was a little off screen. All right, last one. So I've got this. So limit x, y goes to 0, 0, e to the x squared plus y squared minus 1 over x squared plus y squared. Okay, let's try the thing we always try first. If I plug in 0, 0, I'm going to get 0 on the bottom, so I'm not very happy with that. I'm also going to get 0 on the top because e to the 0 is 1. Well, that didn't work. Okay, let's do polar. Limit as r goes to 0. E to the r squared minus 1 over r squared. Okay, so this is a bit of a different situation. Now there's no thetas. On all of the, on the last one we didn't convert to polar, but on the first two, when we converted to polar, there were always thetas left over. Like the first one didn't have r's, but it had thetas. The second one had both r's and thetas. Now we've only got r's and no thetas. So, well, at least I'm not going to have to worry about what theta is or whether it's a bounded function of theta or all that. This is now just a single variable limit. This is like a Calc 1 limit. Well, maybe Calc 2 because we're going to use L'Hopital's rule. So, right. We already know, we can try this again, but we already know that if I plug in r equals 0, it's going to be the same result as if when I plugged in 0 for x and y. It's just going to give me 0 over 0. This is a 0 over 0 form, which justifies the use of L'Hopital's rule. I'm about to take the derivative of the top. Actually, let me do the derivative of the bottom first, because I'm going to do both, and the bottom's easier. Okay, well, now I'm stuck doing the top. So let's do the derivative of the top. Derivative of e to the x is e to the x, so I'm going to just go like that, and I'm using the chain rule, so I have to multiply by the derivative of the inside, so 2r. 1 just turns into a 0 when I do the derivative. So that 0 doesn't do anything. I can ignore it. And then this 2r cancels this 2r. Let me just... So when the smoke clears, we've just got that. And now I start over. And then what is the first thing we always do? I try plugging in the value of r. And at this point, I'm not going to have any problem doing that. E to the 0 is just 1, and so that's our answer. Okay, next we have number 9. Find all first-order partial derivatives of this function. X e to the xyz, x minus y over x plus y. Okay. Partial with respect to x. I'm looking at this thing. This depends on x, this also depends on x. And they're multiplied together. That means I'm going to use the product rule. I do the derivative of this, that's 1. I leave this the way it is. The product rule has 2 parts, and for the next part I'm going to leave the x the way it is and do the derivative of e to the xyz with respect to x. So that's a chain rule. The derivative of e to the whatever is e to the whatever, but I have to multiply by the derivative of the inside. And when I say derivative, I mean with respect to x. The derivative of xyz with respect to x is yz. Okay. And I was not very kind with this one, to be honest. So now I've got this. This is a quotient rule. So this one was product rule. Let's do the quotient rule. So for the quotient rule, the bottom gets squared. So I can get that out of the way. And for the top, I remember it's bottom times derivative of the top minus top times derivative of the bottom. Okay, here is bottom times derivative of the top. And of course, when I say derivative, I still mean with respect to x. So that's just a 1. Minus top times derivative of the bottom, and derivative of the bottom with respect to x is 1. Okay, and I'm not going to simplify that. We could cancel some stuff from the top, but let's just leave our answer the way it is. Okay, let's do the partial with respect to y. When I look at this first thing, at least now I don't really need the product rule, because this x is just going to carry right through. This x is treated as a constant now. I would do the product rule if I had something that depended on y times something else that depended on y, but I would view this right here as a constant times something that depends on y. So this x just carries right through. And then I'm going to do the chain rule to take the derivative of e to the xyz. So that's e to the xyz times the derivative of the inside, and the derivative of xyz with respect to y is xz. Okay, so I'm done with that. Now I just have, I have to do another quotient rule here. Okay, I'm going to do this one faster. The bottom gets squared, and now I go bottom times the derivative of the top with respect to y this time, which is a -1, minus the top times the derivative of the bottom with respect to y this time, which is a 1. So yeah, let me just point out, this and this look almost the same. The main difference is that we have a 1 here and a -1 here. These are not quite the same. One of them is the derivative with respect to x, and one's the derivative with respect to y. Okay. Partial with respect to z. I'm looking at this. Again, I don't need the product rule. this x is a constant. Let's do the derivative of e to the xyz, which is e to the xyz, times the derivative of the inside with respect to z, which is xy. And then I am elated to inform you that we do not need to do the quotient rule again. This does not involve z at all, so this just drops out. So we're done. That's all three partial derivatives. Great. What's next? The Jacobian of this function. Let me just go right into it, I guess. So what is a Jacobian? Basically, this is a vector-valued function, and I see two components here. There's just the comma separating them, right? So that means my Jacobian is going to have two rows. The first row is going to be all possible partial derivatives of my first function. My second row is going to be all possible partial derivatives of my second function. And when I say all partial derivatives, I mean with respect to all possible variables, and there's two variables, x and y. So this is going to be a 2 by 2 matrix. Partial of the first thing with respect to x is 6x plus 4y. Partial of the first thing with respect to y is, okay, this goes away, 4x minus 2y. Okay, I'm done taking partials of this. Let's do partials of this. I'm going to need the chain rule here. To do the derivative of this with respect to x, first I do the derivative of the outside part, so that's a cosine. My eyes got lost. Yeah, cosine 2x plus 3y. Times, because I'm doing the chain rule, times the derivative of the inside with respect to x, which is 2. Okay. Now here I'm going to do the derivative of the same thing with respect to y, which starts out the same. I'm using the chain rule, so I do the derivative of the outside, which is cosine. But then I multiply by the derivative of the inside with respect to y, which is 3. Okay, and that is our Jacobian. Okay, so I'm not doing 11. Let's do 12, and I'll just go ahead and start a new page. We are going to find a tangent plane to this surface at this point. Here's what we want to remember. If we have a level surface, whoops, that's not how the alphabet goes. If we have a level surface, which is taking a function of x, y, and z and setting it equal to a constant, any constant, like this is a function of x, y, and z, and we're setting it equal to a constant. The tangent plane to such a thing is normal to the gradient at the point of tangency. The point that it's tangent at, which is this point. Okay, so let's find the gradient. This is my function. The gradient is just all partial derivatives. So partial with respect to x is 2x. This goes away, and then yz. Partial with respect to y is this goes away, 2y, this goes away, plus xz, because the y disappears. Partial with respect to z is this goes away, 2z plus xy. We are interested in the gradient at the point of tangency, so I'm going to plug in 1, 1, 1. So this is 2 plus 1. In fact, these are all 2 plus 1, right? I'm just going to get 3, 3, 3. And this is my normal vector for my plane. So now I'm good to go. This is where, here, let me, this is like the prototype of a plane equation. I'm going to have to fill in all these blanks. These 3 blanks are the normal vector. 3, 3, 3. These 3 blanks are the point of tangency. 1, 1, 1. I could multiply this out, I can solve it for a variable or whatever, but let's not. This is perfectly fine to just leave as our answer. This is the equation of the tangent plane. Okay, what's next? Lucky number 13. We have a function y minus z squared, z minus x squared, x minus y squared. And we're going to find the divergence and the curl. The formula for divergence that I remember is it's this operator dot product with f. And this is this operator that I sometimes call a fake vector. It's like a vector, but these things that I'm writing inside are not numbers. They are partial derivative symbols. But we find a way to make sense of this. What does dot product normally mean? Dot product normally means I do this times this, plus this times this, plus this times this. But when I say the word times in this context, when I'm talking about this, this operator, or the thing that I informally call a fake vector all the time, this isn't a number. I'm not going to do this number times this number. In this context, times means do the operation that this tells you to do, which is take the partial derivative with respect to x. So instead of doing a dot product where I'm multiplying a number times another number, I'm going to do the partial derivative with respect to x of this, plus the partial derivative with respect to y of this, plus the partial derivative with respect to z of this. That's what we do. And I'm happy to inform you that the partial derivative with respect to x of this is just 0, because this doesn't involve x. And the partial derivative of this with respect to y is just 0, because this doesn't involve y. And the partial derivative of this with respect to z is just 0. So that's very easy once we know what to do. And I mean, it's not always 0, of course. This was sort of a coincidence, but it's not hard even in those cases, because all you have to do is the partial derivative of whatever it is. We just kind of got a little bit lucky and they were all 0. We want to do the curl as well. Curl is this operator cross product f. So how do I do cross products? I go ijk. I'm going to put the first quote-unquote vector here, and I say quote-unquote because this is our friend the fake vector. A real vector would have numbers inside it. This fake vector has these partial derivatives inside it. So I'm just going to put those right across there. And then now I'll put f. So y minus z squared, z minus x squared, x minus y squared. Okay, let's go. I've got my I part times what? So I'm covering this up and I'm going, and okay, let me abuse the word times again. So I'm covering this up. Normally I would do this times this minus this times this, and I'm going to say the same thing about my use of the word times. Times means do this operation in this context. So this means partial derivative with respect to y of that, which was a minus 2y. And then I'm going to subtract this, which means I'm doing the partial with respect to z of this, which is just 1. So far, so good. Minus j times, okay, now I cover this and this. So partial with respect to x of this is 1. And then I'm going to subtract, okay, partial with respect to z of this is negative 2z. Okay, so far so good. Plus k times, all right, cover these up. So I'm doing the partial with respect to x of this, which is negative 2x, minus partial with respect to y of this, which is 1. And I'm running out of space, but I can do this. My I part was negative 2y minus 1. My j part, okay, this turns into a plus, but I've got this minus in front of everything, so that's going to be a minus 1 minus 2z. And then my k part is minus 2x minus 1. Great. Okay, I'm probably going to cut this off and then start a new video.